Oh, hey, welcome back. This is College Algebra, Chapter 10, the final chapter in our sequence of events. And we're talking about sequences and summation notation. So let's begin with a definition for sequences. And a sequence is a function whose domain is a set of integers. So an example of a sequence, 1, 3, 5, 7, blah, 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 2n minus 1, blah, blah, blah. This first guy they're going to say is a sub 1. That's the first term, clearly. And then that's the second term, a sub 2. Et cetera, the third term, fourth term, and this is a sub n, the nth term. It really is, in this format, it's a bit different, because we're used to dealing with like f of x equals 2x plus 1, and then we'll graph it. When we're listing all of these numbers, it makes it seem like it's something new, but it's not really. But anyways, note a sub 1, you could use the nth term formula to figure out what a sub 1 is. So you're just plugging 1 into the formula 2n minus 1, right? So 2 times 1 minus 1 is 2 minus 1, which is 1. Okay, so this a sub 1 notation is basically just the functional notation. So you could write it a of 1, and then it would be 2 times 1 minus 1. But for whatever reasons in the history of mathematics, we've kind of settled on this a sub 1 notation. Okay, so a sub 4, which you could think of as a of 4, to figure out that number, you just plug 4 into this formula. So you'd have 8 minus 1, that equals 7, and of course there, you look up here and there it is. Okay. The entire sequence will be given this kind of notation, curly bracket with the formula for a sub n inside the curly bracket. We can also graph these things, but we usually won't. So, for instance, in our case, a sub 1 is 1, so you just put a dot there. At 2, a sub 2 is 3. I just put a dot there. A sub 3 is 5. So it's a lot like so this is a sub n. It's an awful lot like if you were going to plot f of x equaled 2x minus 1, right? And the old land, the domain was all real numbers. So when you went and plotted the thing, you would end up with a solid line, right? So you would end up with something else like this, as opposed to just a bunch of dots. And that's the deal. That's the definition. The function it's a function just like before, this f of x thing, except the domain is just a set of integers. So you end up with all these dots instead of a solid line. Okay. And then the notation is a little bit different, and usually we present these sequences kind of as 1, 3, 5, like in that form. So it seems like you're doing something new, but not really. Okay, this is actually just a simpler version of what we've been doing with before. Okay. We want to get a bit used to this notation and figuring out terms of a sequence. So in this problem, they want you to write out the first 4 terms of the sequence. So a sub n, the nth term formula, is negative 1/3 to the n. Okay? So they just want a sub 1, a sub 2, a sub 3. And it's easy. You just plug in the little subscript, this 1, wherever you see n. Right? So it's just like f of x, but now you have f of 1, and wherever you see x, you're putting 1. Now we have kind of a sub n is equal to 1. Wherever you see n, you're going to put 1. Okay. so no big deal. A sub 2 will be negative 1/3 squared. Negative 1/3 times negative 1/3 is 1/9. A sub 3 is going to be negative 1/3 cubed. So it'll be negative 1/27. And then a sub 4, negative 1/3 to the 4th. That'll be negative, well, positive 1/81. Okay. Okay, they could look really weird. For instance, this guy, a sub n equals negative 1 to the n plus 1 all over 2 to the n plus 1. So this is, in the world of functions, you usually don't see negative 1 to the x, right? This is kind of new. And the reason why you would do this is if you wanted the terms to alternate in sign. So that, like, one term will be positive, the next term will be negative. I mean, we accomplish this in problem 6 by having that negative on the inside of the parentheses, but you could just use this negative 1 to the n plus 1 to also accomplish this feat. So anyways, let's take a look at the first 4 terms. A sub 1 is negative 1 to the 1 plus 1, which is 2, all over 2 to the 1 plus 1. Negative 1 squared is 1. 2 to the 1 is 2, plus 1 is 3. A sub 2 will give me negative 1 cubed now, all over 2 squared plus 1. So it'll give me the negative, so we're alternating in sign. 2 squared is 4, plus 1 is 5. A sub 3, negative 1 to the 4th, all over 2 cubed plus 1. That turns this guy positive. 8 plus 1 is 9. And then finally, a sub 4, we'll look at negative 1 to the 5th, all over 2 to the 4th plus 1 is negative 1, all over 2 to the 4th is 16, plus 1 is 17. Okay, okay, great. Recursive formulas now. If you know what the Fibonacci sequence is, if you ever heard of that, that's a recursive formula. And it's just a way of defining a sequence where the general formula, the nth term formula, is not given. Okay, the nth term formula, or what they call the general formula, is not given. Okay, so how do these work? You're going to be given kind of what they call a seed value, a beginning place. So here a sub 1 is 5, and then they give you a formula for generating the next term in line. Okay, so the big drawback about this formula is it's hard to kind of just, I want to know what A25 is, right? You can't figure out A25 until you figure out A1, A2, A3, all the way up to A24, because you need the previous one to figure out the next one. Okay, so it's kind of not great. Okay, so they give you a sub 1, and then they have this formula for a sub 2, a sub 3. That's what that for n greater than or equal to 2 means. You don't use the formula to get the first one. Okay, so a sub 1 is 5. We want to get the next couple terms. A sub 2 is going to be 3a sub 2 minus 1. Minus 1, I'm just plugging in 2 wherever I see n in my recursive formula. Okay. Then I could rewrite that as 3a sub 2 minus 1 is 1, minus 1. And then I know what a sub 1 is. That's 5. So 3 times 5 minus 1 is 15 minus 1, which is 14. Okay. A sub 3. So that'll be 3a sub 3 minus 1, which equals 3a sub 2 minus 1, which equals 3 times a sub 2. A sub 2 is 14 minus 1. So that would be 14 times 3, 12, carry the 1, 42 minus 1, which is 41. Let's do one more. A sub 4 is 3 times, basically a sub 3. Let's just cut to the chase, right? Minus 1 equals 3 times 41 minus 1. And if you calculate that out, that's going to be, I believe, 122. Okay. Okay. Great stuff. Let's move on. So we're just basically throwing you a whole mix of things we're going to need here. Factorial notation comes up. Usually you'll see this in probability when you take your statistics. Note how this works. So 5 factorial. It's just a notation for saying 5 times everything below 5. So it's equal to 5 times 4 times 3 times 2 times 1. Okay. 3 factorial. 3 factorial is equal to 3 times 2 times 1. 7 factorial is equal to 7 times 6 times 5 times 4 times 3 times 2 times 1. You get it? You seeing the pattern here? So some of the weirder ones, then 1 factorial is just going to be equal to 1. And then the even weirder, 0 factorial is also equal to 1. If you're wondering why 0 factorial is equal to 1, I suggest you go watch the number file videos on YouTube. Number files video and YouTube. They do a much better job at explaining it than I could. They're a bunch of, I think they're all from Britain or something, who knows. So anyways, if you're really into that, you can go watch the videos on YouTube. Okay. What are some other neat things about factorials? So factorials are kind of recursive themselves. So look, 6 factorial is equal to 6 times 5 times 4 times 3 times 2 times 1, right? 7 factorial is equal to 7 times 6 factorial, right? Because 6 factorial is equal to 6 times 5 times 4 times 3 times 2 times 1. So for any factorial you have, if you have like 10 factorial, you can always rewrite 10 factorial as 10 times 9 factorial. Okay. So in general, the way we write that, the recursive definition for factorials is, if you have n factorial, that'll be equal to n times n minus 1 factorial. And that makes simplifications a lot easier. If you would rather, you can always kind of just do brute force on it and literally write out the entire product. So in general, we can always write n factorial is n times n minus 1 times n minus 2. That's what you're doing above, right? It's just, so 7 factorial is 7 times 7 minus 1 times 7 minus 2, because 7 minus 1 is 6, 7 minus 2 is 5, 7 minus 3 is 4, and then all the way down to 3 times 2 times 1, right? So you could do that if you want to. Why would we even care about doing that? It's because we're going to be called upon to do some simplifications. For example, number 24, 18 factorial all over 16 factorial. And the deal is you probably don't want to write out 18 times 17 times 16 times 15 times 14. I would advise you to use that recursive definition to pull this trick. So 18 factorial is the same as 18 times 17 factorial over 16 factorial, and then 17 factorial I can write as 17 times 16 factorial, right? All over 16 factorial. And once you get that done, you can see, oh, there's a 16 factorial on the top and bottom. We can remove those, and you're left with 18 times 17. And if you multiply that out, that's 306. It's a lot easier than going through this rigmarole of cancellation. But you can always do the cancellation. Nobody's saying you can't. Okay? You could literally sit here and write 18 times 17. I mean, knock yourself out, right? You don't feel like learning anything. You can always do this. Oh boy. myself in over my head here. All right. 4, 3, 1, and then 16, 15, all that junk will cancel out, and you end up with the same answer, of course. All right. They'll also ask you to simplify general formulas, like 2n plus 1 factorial all over 2n factorial. Okay. And again, you could use that recursive definition. So 2n plus 1 factorial is the same as 2n plus 1 times 2n plus 1 minus 1, right? The next term in line, you just subtract 1. So 2n plus 1 minus 1 is just 2n factorial all over 2n factorial. And of course, you end up canceling the 2n factorials, and you're just left with the 2n plus 1. Okay. You could do it brute force, though. 2n plus 1 factorial. Some people would rather do it this way. Equals 2n plus 1 times 2n plus 1 minus 1 is 2n, and then 2n minus another 1, all the way down to 3 times 2 times 1. 2n factorial is 2n times 2n minus 1 times 2n minus 2, all the way down to 3 times 2 times 1. It's the same result. It's just depending on how you view things. Those guys will all cancel, left with the same answer. Okay, so anyways, there's that. Factorials come up in sequences in general. They use them a lot. Let's look at one where we have a sequence. So number 20, a sub n equals n plus 1 factorial all over n squared. I want the first 4 terms as usual. So a sub 1 is 1 plus 1 factorial all over 1 squared. 1 plus 1 is 2. 2 factorial all over 1 squared is 1. 2 factorial is 2 times 1, which is just 2 again. So that's equal to 2. A sub 2. 2 plus 1 factorial, that's 3 factorial all over 3 squared. 3 factorial is 3 times 2 times 1. 3 squared is 3 times 3, of course. I can remove one of the 3's. I get 2 over 3. A sub 3 is 3 plus 1 factorial, that's 4 factorial, all over 3 squared. 4 factorial is 4 times 3 times 2 times 1. 3, wait a second, that should be, oh no, this should have been 2 squared. I apologize. Should have been 2 times 2, so one of the 2's would have canceled, and I would have gotten 3 halves. I'm sorry. Anyways, this guy, 3 times 3, these cancel, you have 8 thirds. Let's do one more. A sub 4 is going to be apparently 5 factorial all over 4 squared. So that's 5 times 4 times 3 times 2 times 1 all over 4 times 4. The 4's will cancel. 2 over 4 is the same as 1 over 2. So you end up with 15 all over 2. And etc. Okay. Okay. So gentle introduction to factorials. The next thing is summation notation, which is a shortcut for writing up large sums. A long time ago, they'd just write it all up, but then somebody came up with the idea, let's just get a formula for this, and that way we don't have to spend a year of our lives writing out numbers. So here we go. The summation notation has this big, ugly Greek capital sigma. I think that's what that is. And all of this material. Okay. So that lower thing, the I, is called the index. And that tells you where you're starting. So this guy starts at 1, and that's called the lower limit. And then it ends at n, and that's called the upper limit. And then this a sub I is a formula where you're plugging in the index values from 1 to n. and you add them all up. So first you let I equal 1, so you would have A sub 1. And then you would let I equal 2, you'd have A sub 2, plus, and you're putting pluses in between every term, plus A sub 3, you let I equal 3. Whoops, I didn't mean to put an equal sign there, sorry about that. And you keep on going, plus dot dot dot, plus all the way up to A sub n. Okay, so let's look at some where we're just expanding the sum and adding it all up. So I equals 1 to 5 of I cubed. Okay. So first you plug in 1, so you have 1 cubed. Then you plug in 2, 2 cubed. Then you plug in 3, 3 cubed. Then you plug in 4, 4 cubed. Then you plug in 5, and that's the upper limit, so you're done. Then you can add them all up. Okay, and it should be 225. Let's look at another, 38. So I have the sum from I equals 3 to 7 of 12. Okay. This formula is constant, so every time you're just plugging in 12. Okay, there's nothing, when I is 3, the thing you're putting in there is just 12. When I is 4, it's just 12. When I is 5, it's just 12. When I is 6, it's just 12. When I is 7, it's just 12. It's a constant. So we have 1, 2, 3, 4, 5 12s. So that'll be 60. Okay. Let's look at another one. This one's a little weird. So I have the sum from I equals 0 to 4 of negative 1 to the I plus 1 all over I plus 1 factorial. Okay. Sometimes it's helpful to write the index down, what the index is at that particular point. So if you plug in 0, you'll have negative 1 to the first power, 0 plus 1 is 1, all over 0 plus 1 factorial, plus, and then you're letting I equal 1 in the formula. So negative 1 to the 1 plus 1 is 2, all over 1 plus 1, 2 factorial. And then you're plugging in I equals 2. So you get negative 1 to the 2 plus 1 is 3, all over 3 factorial. And then plus, we're letting I equal 3, negative 1 to the 4th, all over 4 factorial. And then plus let I equal 4, and we get negative 1 to the 5th, all over 5 factorial. Okay. So it's nice to kind of have those indices there so you know exactly which one, and you don't accidentally undercount or overcount. Here you may think there's only 4 terms because the upper limit is 4, but no, there's 5, right? 0, 1, 2, 3, 4. 1, 2, 3, 4, 5 of them. Okay, let's simplify. So I got negative 1 plus 1/2 minus 1 all over 3 times 2 times 1 is 6, plus 1 all over 24 minus 1 all over 120. Okay. If you put those in your calculator, or if you're ambitious enough to do it by hand, you'll get 19, negative 19 over 30. Okay, so that's expanding sums. We also need to be able to collapse sums. So like number 44. They want you to start your lower limit at 1. Okay, so 44, we have 1 to the 4th plus 2 to the 4th plus 3 to the 4th plus dot 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 plus 12 to the 4th. And I want to rewrite it as a sum, and they're telling me I equals 1 is the starting place. So you kind of have to figure out what goes in here and then what goes up top. You've got to fill in those boxes. Okay, so what goes in the big box? Well, it looks like it's I to the 4th, right? So when I is 1, you get 1 to the 4th. When I is 2, you get 2 to the 4th. When I is 3, you get 3 to the 4th, all the way up to 12, right? When I is 12, you get 12 to the 4th. Let's try another. So here we have 1/3 plus 2/4 plus 3/5 plus dot 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 plus 16 all over 16 plus 2. And again, they tell us to start I equals 1, and then we got to figure out the upper limit and the formula. Okay, the formula will be in terms of I, of course. Okay, so it looks like in the top, in the numerator, it's going 1, 2, 3, all the way up to 16, right? So if I just put I there, I think that'll do the job. And then in the denominator, it looks like it's I plus 2, right? Because when you have 2 in the top, it'll be 2 plus 2 is 4. When you have 3 in the top, it'll be 3 plus 2 is 5. And then it goes all the way up to, it looks like 16. Okay. Let's try one more, and we'll leave it at that. This one is foreshadowing. If you've taken your English Lit class, you know what foreshadowing is. Plus dot 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 plus AR to the n minus 1. It's a little harder, but it's leading somewhere. Okay, so I equals 1 to something. So the formula, you can see it, the numbers on the exponent. So you see how it's 1 and then 2 and then all the way up to n minus 1. The exponent on the first one, although you can't see it, you could imagine it's 0 because r to the 0 is just 1, right? So our formula is going to be AR to the some sort of I, but you can't use I because I begins at 1, and we want I to begin at 0. So what if we put I minus 1? Is that going to work? So when I put in I equals 1, I'll have AR to the 0. When I put in I equals 2, I'll have AR to the 1. I equals 3 will be AR to the 3 minus 1, which is 2. Yeah, so it's working, right? You're getting these particular elements back out. And then our last element we want to be, I guess, if you put in n, right? So if I equals n, you would get AR to the n minus 1. And so that would be our formula. Okay. Okay, so just kind of a gentle introduction to sequences and summation notation. In the next 2 videos, we'll take a look at 2 particular types of sequences that we use in mathematics, the arithmetic sequence and the geometric sequence. We'll also worry about adding them up. Okay, thanks for watching, and we'll see you next time.